All right, this video is going to talk about verifying trig identities. And we've talked a little bit about this previously, but that's the main idea, and we're going to get some pretty messy ones. Main idea of this section here. So this video is just going to give us a few recommendations when you're going to verify identities, a couple of different things that you can try. Because again, sitting idle and just staring at it isn't really going to get us anywhere. So what we want to do is make sure that we're taking a good approach. We're trying to use the ideas that we know, things that we've maybe seen before, and take advantage of some easy ideas. So looking at it, number one, the first best recommendation is to work one side at a time. Remember, we're not actually solving an equation right now. So we're not supposed to use the rules of equality. I can add things to both sides or multiply things on both sides, keeping things balanced. What we really want to do is ignore the fact that both sides are even really there. Or at least, bare minimum, prove that one side equals the other side without letting those sides interact. So one idea would be taking a look at the statement we have. Tangent of pi over 2 minus x reminds me of those old cofunction identities, right? The tangent of pi over 2 minus x is really the same thing as the cotangent of x. It's cofunction partner. So one thing I might do is just take that left side and let's replace it. Let's take out that tangent and we'll replace it with cotangent of a simpler just x, x being our angle. Well, in that case, now I see a lot of reciprocals. So what I might do is take those reciprocals and let's convert them. Let's make some fractions out of this because sometimes we get lucky and things might disappear for us. I know that the cotangent is equal to the cosine over the sine of x. I also know that the secant is equal to 1 over the cosine of x. And while we're at it, like I said, you only have to work one side at a time, but it doesn't mean we can't change both sides. We could convert this cosecant into 1 over the sine of x. Now, without actually crossing it out, again, I'm going to use a highlighter. Cosine of x on the top will cancel with cosine of x on the bottom, and we really end up with 1 over the sine of x is equal to 1 over the sine of x. And make sure you write those statements out because nobody can dispute that 1 over the sine equals 1 over the sine as long as they're the same angle. Therefore, QED, quid ergo demonstratum, we've proven what we wanted to prove. The left side equals the right side. And if those last statement is the same, then that means that the first statement is also a true statement. It's also the same on both sides. A second recommendation is look for algebraic opportunities, things like that canceling those fractions that we just looked at before, if something's in the numerator and the denominator. Or, looking at the statement we have here, notice on the right side we have just a term, 2 times the secant squared. There's no adding going on. But in the middle of this left side, we're adding 2 fractions. Well, the only way to add fractions is with a common denominator. So one recommendation would be, let's go ahead and take and find a common denominator. Well, if there's a 1 plus the sign in the fraction on the left, why not multiply 1 plus the sine of alpha? And remember, keep that variable the same. If they start you with alpha, then we write alpha. But again, 1 plus the sine over 1 plus the sine is really equal to 1. But I can multiply that by what I already have. Plus, I already have 1 plus the sine of alpha. So why not multiply by 1 minus the sine of alpha? Now, I can keep rewriting the 2 secant squared of alpha, but I'm going to go ahead and do some of the work here and see if I just can't end up there without having to rewrite that over and over and over again. Again, on the left, we have 1 times 1 plus the sine of alpha. On the right side, on the top of the fraction, we'll have 1 times 1 minus the sine of alpha. And in the denominator, don't we have the same statements? 1 plus the sine times 1 minus the sine? Or basically 1 minus the sine squared. If we FOIL those out, that's that difference of squares, right? 1 plus the sine times 1 minus the sine is 1 minus the sine squared. Well, taking a look at what we have on top, we have a positive sign and a negative sign. So again, plus sine alpha minus sine alpha should disappear. We otherwise have 1 plus 1 is 2. And on the bottom, 1 minus sine squared, remember, is our good friend, the Pythagorean identity. 1 minus sine squared is cosine squared. Well, anything over the cosine is really 1 over the secant, right? Thinking that as that reciprocal. So we can call this 2. Cosine would flip to the top and be called secant of alpha. Only it was another cosine, which also flips up, or cosine squared becomes secant squared. And I would say that this, again, was what we wanted to prove. That's exactly what we wanted to be equal to up here at the top. Again, algebraic opportunities like adding fractions, those difference squares, right? 1 plus and 1 minus the signs. Those are very helpful things. Having monomial denominators, right? That cosine squared that we ended up with down here. All those things can be very helpful for us in the end. 2 good rules. We've kind of used a couple of them already. Look for opportunities to use easy identities like reciprocals, such as the secant being 1 over, again, the cosine. Also, converting to sines and cosines can be very helpful. Like we did on the first screen, oftentimes if we can do that, we can make easier statements for ourselves. So things like the sine of x is really multiplied by the tangent. Well, remember, tangent is sine over cosine, which means on the right side here, we really have sine squared over cosine. On the left, well, notice that subtraction again. Why not try to combine those? Let's think about common denominators. I already have a cosine in the first fraction, right? 1 over the cosine. So why not multiply top and bottom of that second fraction? If I multiply the bottom, I'll have cosine of x. And on the top, that would make cosine squared of x. Well, 1 minus cosine squared is really sine squared. And sine squared of x over cosine of x is equal to sine squared of x over cosine of x. Therefore, again, Q, E, D. We're all good. The last recommendation I can give you, again, things like sines and cosines are helpful, basic trig identities, basic algebra steps, work only one side at a time, and if all else fails, do something. Such as on this statement here. Now notice I've got some subtraction in both of them, so I really don't want to lose that part. But again, a monomial denominator here on the bottom, I can take advantage of that. Maybe I can distribute that. So why not call this the cosine of x over the cotangent of x. Right? And cotangent divided by cotangent is really just 1. And notice how much closer we are to a final answer already. Right? Let's go ahead and write that so we can actually read it here real quick. Again, cosine on the top, cotangent on the bottom. Well, cotangent doesn't really relate to sines and cosines too well, so why don't we do a little fancy work? Cotangent is really the cosine over the sine. In that case, let's multiply by the reciprocal. We've got cosine of x on the top. I'm going to take this fraction on the bottom and multiply sine x on the top, cosine x on the bottom. And finally, cancel those cosines. And the sine of x minus 1 equals the sine of x minus 1. And therefore, QED, we proved what we wanted to prove. All right, I hope that helps you with verifying trig identities. If you have any questions, make sure you talk to your teacher. But again, the biggest recommendation, make sure you try something. Do something. Do some substitution, add like terms, think about common denominators. How can you convert, right, without crossing that equal sign? Notice we never changed the right side here. Without crossing that equal sign, how can you convert the left into the right? Or vice versa. Have a great day.